Hi everyone, I'm gonna now cover a Lagrange polynomial interpolation. Just finding my mouth, there we go. Yeah, we're gonna cover Lagrange polynomial interpolation. As per usual, I'm gonna do a very quick theory video, just covering the underlying theory of it. But I'm not gonna go into too much detail as to why this works or how, but I'm gonna show you how the equations are formed. I'm not going to go into why because that's a bit too much to cover right now, and it's not going to really benefit you understanding the intricate mechanics of it. But anyway, let's get on with this. So what we're wanting to do, again, we're creating a polynomial. So we're going to be creating a y equals, I'm going to call it Pn as before, so Pn of xi. So it's a polynomial where we're wanting to know what the value is at xi. So that we're going to be getting a0 plus a1 xi plus a2 xi squared plus a3 xi cubed and so forth up to an xi n minus 1. So that is what we're wanting to get eventually. Sorry, that's not xn minus 1, that's just xn, because we started on 0, so that will end up being just xn. So this is what we're wanting to get at some kind of polynomial. We've already gone through the Newton methods, whether it's the divided difference, the forward difference, backwards difference. This is another method that's similar to one of those, but we are looking to get a polynomial. So let's start by defining what are our different terms. Well, we're wanting to get this Pn. Lagrange's Pn, so this is Pn for Lagrange, of x is equal to, by definition, this is what I was talking about. I'm not going to go through how or why this lands up working, other than maybe a very brief cover, but it's going to be, Pn is going to be the sum of from I equals 0 to n of yi multiplied by, I'm going to call it Li of x. So in order to do this, we need to know what Li of x is. We should have our y, because this is the whole purpose of this polynomial interpolation, is when we have a value of x, a series of values of x, and a series of values of y. But what is our Lix? Well, if we break this down, our Li of x, again, this is by definition, it's going to be equal to, so I'm going to use this symbol here. It's a big pi. So like we have the sigma there, this big pi, I'm going to go j equals 0 through to n. The big pi means where sum is whatever's contained within it, you increment your I up from I through to n, and you add up each term. The big pi is you're going to increment each item, which is subscript j, up to n, and instead of adding them like with the sigma, you're going to multiply them with this. So this is going to be x minus xj divided by xi minus xj. Now, this whole sigma, we are going to be putting in an extra proviso. Because we have xi minus xj in the denominator, we need to put a proviso going for all i's not equal to j. So if I is equal to 2 and n is equal to 5, we will land up multiplying all of them except for our x2, where I is 2 and then j is 2, so we will exclude this whole term when it comes to that. And you'll see what I'm talking about as we continue. So if I break this up, I'm going to just show you what it looks like below. So we would land up with x minus x0 divided by xi minus x0 multiplied by x minus x1 over xi minus I minus x1 multiplied by... Okay, actually the multiply is going to get confusing. I'll just use a dot. Oh, actually I can just omit. Let me pull back my pen. I'll use a dot. So multiplied by that, multiplied by... So I'm going to go dot, dot, dot. Let's say that we continue through to x minus xi minus 1 over xi minus xi minus 1 multiplied by... This is... So then where our j hits our I, we will end up going... We'll skip that one and go to x minus xi plus 1 over xi minus xi plus 1. And we will then land up continuing until we land up with x minus xn over xi minus xn. So that is roughly what we're looking at. I wanted to just illustrate this because it's important to remember you aren't just omitting the denominator, you're omitting the numerator and the denominator of that term. So let's break it down a bit further. So we have now determined what our Li is, so we've got that. We will have our Yi, and we can now determine what our Pn is. So if we're given a series of data for, let's go n, let's go n, let's go x, and let's go f of x. So if we land up with 0, I'm going to do just 3 terms. So 0, 1, and 2. And we have x0, x1, x2. And this will be, let's call this y0, y1, y2. So y0, y1, and to move down, y2. We need to determine, because our polynomial is a sigma function, because we are summing up the y multiplied by the li for each of these terms. So our li here, remember our I in this case is dictated by that. So let's work out our L0. So our L0 is going to be L0. Let's go L0. We have, just going to scroll up so we can see what's going on. Let me copy it so that we can see nicely what's right next to it. So what we have with our L0 is, and we know that our n goes up to 2. We have 0, 1, and 2. So our L0 is going to be x minus, so that's xi, so that's going to be x0 in this case, divided by our xi, again, is going to be x0 minus xj. Well, we know that j can't equal xi by our statement here, so our first term is going to be x0 minus x1 as our first j. My mistake. The top value, that is not an I, that is a j over there. So that is x minus x1 over x0 minus x1. Then that's going to be multiplied by our next term, which will have x minus x2 for j equals 2 over x0 minus x2. And that will give us our L0. Our L1, similarly, would be x minus x0 divided by, so this is going to be, our xi is going to be an x1 minus x0, multiplied by our next term, we're going to have x minus, now we can't have x1 minus x1, so we'll have x minus x2 divided by x1 minus x2. And then you can see where I'm going with this. Our L3 will have the same first term here, it'll be x minus x, So let me just put down our L3. Our L3 would be x minus x0 divided by x2. So this is our L2. x2 minus x0, and then we would have our next, which is x minus x1 divided by x2 minus x1. And we wouldn't have a last term, otherwise we'll have 0 in the denominator. So that is how we work out our L's. And then we just multiply that by our y's and add each of those up. And if you were to multiply these out, you would get a polynomial in this form. Otherwise, you just have it factored. Now, the way that you can think of it, just as a brief understanding of how it works, consider each of these. So let's consider, this is an approximation method. So let's consider when x is 0. So we have each of these terms. So this one's going to be multiplied by y0. So our polynomial is going to have L0 multiplied by y0. If we consider that, well, when x is x0, we'll have x0 minus x1. This denominator is all constants, but our top we will land up having x0 minus x1, x0 minus x2. So this is going to land up being a number that we land up with. And our y, we will land up with just our y0. So our L0 term is the only term that lands up having something, because if we look at all our other terms, when x0, for our next one, we'll have L1 times our our y1. So x0, we land up with a 0 in the numerator, and again with L2. So our only term that we would land up having is this term over here. And what we land up with is x0 minus x1, which cancels with this, and then x0 minus x2, which cancels with this. That leaves 1 times 1 times our y0. All our other terms become 0, such that we land up with just y0 is f of x0 equals y0. And once again, you can consider the same for x1. So if we plug x1 in here, we have a 0 in the numerator. Plug x1 in here, we have a 0 in the numerator. Plug x1 in here, we have x1 minus x0, cancels with this. x1 minus x2 cancels with this. So we have 1 times our y1. So with that, we land with only y1. That's roughly how it works. I'm not going to go into the specifics exactly how this was all broken up and determined, but this should give you a good feel for how it works. I'm going to go over a couple of examples in the next video.